so we're going to go ahead now and look at question 4. Now, question 4 is the only one where it's more of a thinking question. So the weight of the body above the Earth's surface is inversely proportional to the square of its distance from the center of the Earth. What is the effect on the weight when the distance is multiplied by 2? So let's try to first set up what our equation is going to look like. The weight of a body above the Earth's surface is inversely proportional. So what does that mean? That means we divide, right? Inversely proportional to what? Square of the distance. So that means my weight is going to be k, which is our constant, over the distance squared. So that's our formula. Now, we want to find out what happens when we double our distance. So we want to find out what's going to happen when we double our distance. So let's plug some numbers in so we can see what's happening here. Okay, I'm just going to plug in a value for the distance. So let's let the distance be 1 and see what happens. Okay, so if your distance is 1, what is my weight going to look like? Okay, so the weight, if I use a distance of 1, well, that means k over 1 squared, which is then your weight is k, right? Okay, so if I have a distance of 1, my weight is whatever the constant is. Now, what happens if I double the distance? Well, if I double 1, what am I going to use then? Okay, if I'm going to double the distance, then that means we're going to use a distance of 2, right? And if I plug that in, let's see what happens, okay? So we're going to look, I want you to look at this right here when your distance was 1, and I want you to see what happens when your distance is 2. Well, that's going to be k over 2 squared, right? And we know that 2 squared is then what? 2 squared is 4. Now, what happened here? Let's look at these. So this one was my original, and when I doubled the distance, what happened to the denominator? The denominator wasn't half anymore, was it? What did it become? 4. Why? Because you squared it. Okay? So what happened to the weight? When I doubled the distance, what happened to the weight? The weight becomes 1/4 as much, right? Because we went from it being k to k over 4. So the weight is 1/4 as much, right? Because what happened when you have that, when you doubled it, you're not really doubling it, you're putting it in, you're squaring it. Because 2 squared then makes it a 4. And so when you compare them, this one's k, and this one's k over 4. So when you double the distance, the weight is only 1/4 as much. Because that distance was what? In your original, that distance was squared. So that's what I'm looking for. When you double the distance, your weight is only 1/4 as much because of the square factor. Question 6 is next. And question 6 is a joint variation question. Oh, wait, let's see. Question, sorry, 7 is the joint variation. One of these is joint variation. 8 is. Yeah, 8 we'll look at later, but 8 is joint variation. So let's look at question 6 first. Okay. Question 6 is inverse. So we're looking at question 6. The weight of a person on or above the surface of the earth varies inversely. Okay, so what does that mean? That means we divide. So varies inversely as the square of the distance the person is from the center of the earth. So what does our formula look like? It says it varies inversely as the square of the distance. So it's going to look just like the last one. The weight is going to equal K. Now, K is our constant. And that's going to be over the distance what? Distance squared. Now, they give you some information because we're going to have to find K. Right, so unlike the last one, it was a theoretical question. This one, though, we need to actually find the value of K so that we can answer the question. And what do they give you for question 6? If a person weighs 180 pounds on the surface of the earth and the radius of the earth is 3,900 miles. Okay, so the weight is going to be that 180 pounds. And that person is from the center of the earth a distance of 3,900. Okay, so that's what we've got. We've got the weight, 180 pounds. Distance to the center of the earth is the radius, which is that 3,900. Now we're going to plug our values in and we're going to find our K. So 180 equals K over 3,900, and don't forget to square it. So now that gives me 180 equals K over 3,900 squared, which is then this. Okay, so that's that when I squared it. Now, how do we finish it? We simply do what? Cross multiply. Okay, so I'm going to multiply that by my 180. And that gives you a huge number for K. And that's 27378. And then it looks like 1, 2, 3, 4, 5 zeros. So there is your value of K. Now, why is K so large? Well, K is so large because of the earth and it being so large. Also, when we get a little bit further from the earth, our weight doesn't really change much. That's because the K is so high. Because if you're up on an airplane, you're further from the center of the earth, but your weight doesn't change much at all. You weigh almost exactly the same, but you do weigh a little bit less than an airplane. But when you get to outer space, it changes quite a bit, right? Because that's way far out. The closer you are to Earth, the more of an impact it has on your weight. The closer you are to the center of the Earth, the more that you actually weigh. And our formula now is this. So the weight is going to equal K, which is this huge number. And again, these numbers are pretty large over the distance squared. So that's our formula. Now, we want to plug in some new values. So what do we have now? It says, what will the person weigh if he or she is 150 miles above the Earth's surface? So the weight of a person on or above the Earth's surface varies inversely as a proportion square of the distance from the center of the Earth. If a person weighs 180 pounds on the surface of the Earth, the radius is 3,900. Okay, so it's 3,900 to the center of the Earth. What will a person weigh if he or she is 150 miles above the Earth's surface? Well, how far are you from the center of the Earth? You're a long ways from the center of the earth because you are 3,900 miles away. We're going to have to add on 150 miles. So this is how far you are now from the center of the earth. So 3,900, we're going to add on 150. So you're 40, 50. Okay, so 4,050 miles away. So we really haven't changed a lot. Now, if you're 150 miles away from the Earth, from the center, you're still going to weigh quite a bit. So let's find our new weight. So 27378 and all those zeros. Okay, we just have to use a calculator here. And we're going to divide that by 4050 squared. Okay, and so let's see what we get for my weight now. See what we've got. So we've got, and I'll put it up here so we can see, we've got 27378 and then 5 zeros. 2, 3, 4, 5. You could use scientific notation if you wanted. We're going to divide that by 4050 squared. And that's going to give me now 100 and, how far does it say to round here? It says round to the nearest tenth, or sorry, round to the nearest hundredth of a pound. So that's 66 point, if we round, tenths is 1, hundredths is 2, so it looks like 9 1 pounds. So you really haven't changed much, right? Your weight really has not changed a lot. Because this is how far you are from the center of the Earth. You only went up 150 miles. In the grand scheme of things, that's only going to change you a little bit. Okay, so that was question 6. Next, we'll look at question 7. And then we'll look at question 8. Question 7. Now, question 7 is a joint variation. Whenever we see inversely, we divide. Okay, if it doesn't say anything, then we multiply. So the volume of a gas varies inversely as the pressure. And directly, that means we multiply as the temperature. So what does our formula look like? Well, we're starting off with the volume. And the volume is going to equal K. And what are we going to multiply that by? We're going to multiply that inversely by the pressure. So inversely by the pressure means the pressure is below. And directly by the temperature, so that means my temperature goes on the top. So there's our formula, right? Volume equals K times the temperature. Divide that by the pressure. Now, what do we know? The volume that they give you, that this gas occupies, is 2.2. Okay, so there's our volume. The temperature is 340 degrees in Kelvin. And again, Kelvin is something that we don't use, but in a physical science class or a physics class, you may use Kelvin. We either use the Celsius or the Fahrenheit temperature, depending upon where you're from, but either Fahrenheit or Celsius. There is also Kelvin. Kelvin is something that is reserved for your science classes. Pressure of 16 newtons. And now we can plug our values in and we can find our K. So our volume is 2.2, and that's going to equal now K times 340 over the pressure, which is 16. I'm going to simply cross multiply here. And when we cross multiply, we now get 16 times that 2.2, which is 35.2. And that is going to equal 340K. Divide by your 340. And so my constant K is now, we'll take it out to 3 places. That should be more than enough. My constant K is 0.1 Close enough. Okay, 4 places should be more than enough. You could probably get by with 3, but I'll go ahead and write that out to 4. Is everyone okay with how I did that? Right? So we just cross multiplied, we got our K. Now, rewriting, we have our volume equals 0.1035 times the temperature divided by the pressure. Now, K can be a different number depending upon the different type of gas that you're working with. You know, that K might be something completely different if it's helium versus if it's hydrogen or versus if it's neon. So each gas has its own K. The relations are the same, but the K can change based upon the gas. Because something like our normal atmosphere is going to have a way different K value than whatever this gas is. Now, what do we know here? We need to find the volume when the temperature is 306 and the pressure is 24. Okay, so we now need to rework this and find the new volume when we change the pressure and we change the temperature. So the temperature got dropped a little bit, and the pressure went up. And so what's going to happen to our volume here? Well, we've got our K. We're going to multiply that by 306, divide that by our 24, and we should end up now with approximately 1.3. When we work that all out, we end up with a new volume of 1.32, and that is going to be in terms of liters. So is everyone kind of okay with how I set that up? And in some cases, K can be a really, really small number, K can be a huge number, or K might be a whole number, a small whole number. So it just depends upon what you're working with. If you're working with something like gravity, your K is going to be a really, really large number, because the Earth is so large. On this one, it was pretty small because whatever gas you're working with, that's your constant value. So let's now go ahead and look at question 8. And question 8 is like question 7. It's another joint variation question. And on this one, we're looking at trying to keep a car from skidding around a curve. Now, when we look at trying to keep a car on the road, there's lots of different things that go into this. How heavy the car is, right? Because if a car is really heavy, it's going to be a lot easier to go around a curve. If it's really light, it's going to want to slide around. Okay, so the weight of the car is important. Also, what's really, really important, though, is how fast the car is going. Because the faster the car is going, the more likely the car is not going to be able to make this curve and it's going to spin out. The weight is going to help keep the car on the road. The speed of the car, though, itself is really going to make the big difference. And that's why that part is squared. So let's look now at question 8. The force needed to keep a car from skidding on a curve varies jointly as the weight of the car and the square of the car's speed, and inversely as the radius of the curve. If a force of 3,600 pounds is needed to keep an 1,800-pound car traveling at 20 miles an hour from skidding on a radius of 600 feet, what would the force be required for a curve of 640 feet at 50 miles an hour? So let's make up our equation first. We'll plug our values in, and we'll find our K. So what are we looking at? We are looking at the force that is going to be required to keep this car from skidding out of control. So that's going to be your force here. Now, what relates to that. It says, the force needed to keep the car from skidding varies jointly as the weight of the car and square of the car's speed. So we've got a K, and we're going to multiply that by the weight of the car and the speed. But the speed is squared, and then we're going to divide that by the radius because it's inverse. So we're going to divide that by the radius of the curve. Right? The more wide the curve is, the easier it's going to be to keep the car on there. But the main thing that decides whether or not the car is going to spin out or not on that curve is the speed. Speed makes the biggest difference. Weight has some factors too, but the speed is the biggest part. Now let's see what we've got. We want to keep this car from speeding. The force is 3,600. So that's your force. The car weighs 1,800 pounds. It's traveling at only 20 miles an hour. And it has a radius of 600 feet. We're going to find our K. So that's 3,600 equals now K times the weight, which is 1,800, times the speed, but we've got to square it, so that's 20 squared over the 600. We're going to find the K, but K can change because K might be different depending upon the road conditions. So as we know, it's a lot easier to skid out when it's raining outside or when it's icy, right? So it would have a completely different K. This K is whatever conditions it's based on, whatever the road conditions are of that day. Now that K might be different tomorrow, right? Because K might be different if there's ice on the road or if there's water on the road. So that's why K is something that you find, but it changes depending upon the road conditions. So let's go ahead and find our K for this piece. So we've got our 1,800, and we're going to multiply that by 20, and we have to square it. So that gives me now, when I rewrite, 3,600 equals 720,000 over 600. Okay, so we're going to go ahead and cross multiply so that we can find our K. So we'll cross multiply here. So 3,600 times the 600, and that gives you this. Yeah, it looks like 1, 2, 3, 4 zeros equals 72000. Okay. Yep. And we're going to go ahead and divide out, and we're going to get our K. So let's divide that out and see what we get now. Looks like K is going to come out to be a value of 3, doesn't it? Okay, so there's your value of K there. Now, when we rewrite this, we want to change our conditions and recalculate. So now we're going to rewrite our formula. And our force now is going to equal 3 times the weight times the speed squared over the radius of the curve. And what do we know about the parts? What do they give you now? Okay, they say, what force is required to keep the same car from skidding on a curve with a radius of 640 feet? And a speed of 50 miles an hour. Now, what's the weight of the car? Does anyone know what the weight of the car is? That's given in the question. Not directly, but can someone tell me what the weight of the car would be? What did we have of the weight of the car before? 1,800, right? And it's the same car, right? So the weight has to still stay the same. So the weight is still going to be 1,800, right? So I want to just point that out. So you'd see it says it's the same car, so that means the weight didn't change at all. The force to keep this car from skidding is going to be substantially more. And why do you think that's going to be substantially more? Because that speed is higher, right? And what changes the most? The speed, because it's what? Squared. When you square something, it makes a big difference. So the radius of the curve is not nearly as important as the speed. When you increase the speed of that car, to try and hold it on the road requires a lot more force. So let's go ahead and multiply. Okay, and I'll just go ahead and divide it all out. We'll just work it out here. And it looks like it's going to take 21,000, and if we round to the nearest pound, 94, and these are, what's it measured in? Pounds. So it takes 21,000 pounds instead of that 3,600 pounds. And why is it such a big difference? Because we went from 20 miles an hour to what? 50 miles an hour. Think about it in a car. We know if the roads are icy and you start driving very fast at all, it becomes really, really hard to control the car, right? I mean, the difference between 20 and 40 on a car on ice is dramatic. It's a huge amount because it's squared. So that's why speed is such a big, important factor when you drive on a wet or an icy road. Speed is more important than anything else because it's squared, so it has the biggest impact. Did we have any other questions out of 3.7 to look at? Anything else? Well, if not, then we're going to go ahead and start and work through 4.1. And 4.1 is inverses. And some functions have an inverse, some functions do not. And if you say this, f with a negative 1 here, that is said f inverse of x. Okay, so that little negative 1 is your inverse. It's the opposite. Now in mathematics, most things have opposites. Addition has its opposite subtraction. Multiplication has its opposite division. When we talk about functions, though, some functions have an opposite and some functions do not. And what does an inverse look like? Well, an inverse, you have to be able to fold it across the line y equals x. So let me show you what two functions are that are inverses. We'll do a very simple one. I want you to visibly see what an inverse is. These two functions are going to be inverses of each other. And so this one, we'll call this one f of x, and this one is f inverse of x. Now, for them to be able to be inverses, they have to be reflectable around the line y equals x. So look at what happens when I fold them over. this point, if I'm right here on this graph, okay, every point is going to match up. This point here, if I fold it across the dotted line, see, it's going to match there. This point would match up down there. All of it matches up because every piece folds over. So it folds over that dotted line. Here's another example. These are called inverses. Okay, so they're inverses because if I fold it across this dotted line, this diagonal here, they match up. So this part on this graph, the F inverse, matches up there, right? This one, if I fold it over, matches there. That piece matches there. So these are inverses. So this is graphically what an inverse looks like. Here's another one. Here's another one that's an inverse. These are also inverses. And I'll try to draw these as best as I can here. Now these are also inverses, because if I draw my same line, y equals x, if this is your inverse, this is your f here, what's going to happen? This piece here, this x here, folds across and matches there. This piece folds across and matches there. That one folds across, right? That folds and folds over. So as long as you can fold it over, that makes these inverses. So these two functions are inverses of each other. Now the next one is not going to be an inverse. So let's see why this one is not an inverse. And again, I'm just trying to explain to you what an inverse is and what an inverse is not. Okay, why would this one not be an inverse? Let's talk about this here. Right, because, okay, if I try to flip this piece here, let's say I'm right here. Let's look at this x. Okay, if I fold it across the dotted line, where's it going to fold out to? Yeah, it's not going to be on that line anymore, is it? Right? It won't match up to the line. So these are not inverses. Why are they not inverses? Because if I'm here and I fold across this dotted line, y equals x, your identity function, right? Right here, the diagonal line. If I'm right here, this piece wouldn't fold over. If I folded it over, right, fold it over, it's going to be down there. And it's not going to be on that graph anymore, is it? Right? So for it to be an inverse, you have to be able to fold it across the line y equals x. You can also look at it as compositions. If you compose two functions together and they give you out an x, that means they're inverses. But I'm not going to do the composition because I don't think it's that important. We're just learning the basics, and we're doing it graphically instead of doing the composition. But now not all functions have an inverse. So that's what an inverse is. You have to be able to slide it over. You have to be able to fold it across and match it up. Not all functions have inverses. And how we tell graphically if a function has an inverse is we use the horizontal line test. And what we do for the horizontal line test is we draw horizontal lines. If any line touches the graph at more than one place, it is not one-to-one and has no inverse. So remember when we did the vertical line test, right? And the vertical line test told you if something was a function or not, right? Very simple to do. And you just drew your vertical lines, and if any line touched the graph at more than one place, it wasn't a function. Well, the horizontal line test, it works with inverses. Now, 1 to 1 means it has an inverse. So 1 to 1 is the same as saying that function has an inverse. They're the same. So sometimes you'll see the textbook talk about 1 to 1, and sometimes you'll hear talk about the inverse. Okay? Inverse and 1 to 1 are the same. If it's 1 to 1, it has an inverse. So let's look at a few graphs and see if these graphs have an inverse and are 1 to 1. So let's look at a common one. Let's talk about a cube. Does a cube have an inverse? Well, let's draw a cube and see if a cubic graph has an inverse. Here's a cube. Does this have an inverse? Yes or no? Yep, because we draw horizontal lines, right? Each horizontal line touches at only one place, so this is 1 to 1. And it has an inverse. We'll be finding those inverses here in a moment. Let's look at another one. What about a square? A square is a common graph. Does a square have an inverse? Squaring function like this. Does this have an inverse? Yes or no? Draw horizontal, not vertical lines. Okay, and if you draw a horizontal line, what happens there? It crosses at more than one place. So if it crosses at more than one place, it is not 1 to 1. And it has no inverse. So that one does not have an inverse because it fails the horizontal line test. Let's do one more, just to make sure we understand this completely. What about a square root? What about a square root graph? Does that one have an inverse? Yeah, because if you draw lines, none of those lines touch the graph at more than one place. So that means this is 1 to 1 and has an inverse. So we've kind of talked about what inverses are graphically, and we've seen how to see if a function has an inverse or not. Right, graphically. Now let's try to find the inverse of a function. And I'm going to give us one that we can find the inverse of pretty easily. And then we're going to graph it so you see it really does have an inverse. So there's a step-by-step procedure that we need to follow to find the inverse. So we're going to be learning how to find the inverse. And step number 1 is check to see if the inverse exists. And x squared has no inverse. Unless the domain is specified. Which we'll look at one of those here in a moment. So check to see if the inverse exists. Now, most functions have an inverse. The exception to that is x squared. an x squared has no inverse because it's a u. Unless it has a specific domain. And sometimes they cut off the x squared and they tell you it has a certain domain, so then it would pass the vertical line, the horizontal line test. But in general, if there's no domain given, no value of x given, then it will not have an inverse for the x squared. Now, if it has an inverse, here's how we find it. Step number 2, you replace f of x with y. Step number 3, you swap or interchange x and y. So you flip them around, you swap them out. Step number 4 is you solve for y and replace y with f inverse of x. So this is the procedure here. So check to see if the inverse exists. Now most of these have an inverse, and most of the time that inverse exists. There are a few exceptions with the x squared, right? Because the squaring function fails the horizontal line test. Now, once you determine that the inverse does exist, then what you need to do is replace that f of x with your y, switch out your x and your y. So y becomes x becomes y, resolve it for y, and then replace y with f inverse of x. So here's one that we're going to be graphing, and we're going to make a very simple one to begin with so you can see what, again, an inverse looks like. So this one, we're going to be finding the inverse, and we're going to graph it too. So I want you to find the inverse of this function. This one has an inverse, right? It's not squared. Basically, anything that's not a square has an inverse. And a square can have an inverse if they limit the domain, which I'll show you some of those here in a moment. But let's just start off with a very, very basic one. We're going to find the inverse, and we're going to graph that inverse and the function so you can, again, relate the functions to their graph. So that has an inverse. Let's find it. So step number 1 is you replace y with f of x. Or sorry, f of x with y. So that's what we did. Now what do? Okay, now we swap out, or we interchange the x and the y. So x becomes y, and y becomes x. So we switch them around. So x and y flip places. Now we solve it for y. So we're going to go ahead and solve this for y. So I'm going to add my 4. And how do we get rid of a cube? Does anyone remember how we get rid of a cube? Not square root, because it's a cube. You were on the right track, though. Square root gets rid of a square, right? So what gets rid of a cube? Cube root. So now we can replace that y with f of x. So we'll rewrite it once more with the y. So y equals now the cube root of x plus 4. And so f inverse, which is our inverse function here, f inverse of x is the cube root of x plus 4. Now, we have graphed both of these functions before. Okay, let's go ahead and graph these. We have done them. We know how to graph them. I'll graph one of them in blue, one of them in green. So if I was going to graph this one here, my f of x, what would that minus 4 make the graph do? Not right 4. Remember, it's on the end, and it's negative. So that would force it what? Down 4. So that's 1, 2, 3, 4. And what does that look like? All right, it looks like a cube, doesn't it? So the cube graph looks like that, doesn't it? Is everyone okay with that? So that's my cube graph. Now, what about the cube root? Okay, well, what does that 4 do in here? That 4 is inside the cube root. It's positive, so that makes it do what? That makes it move back to the left 4. And what does a cube root graph look like? It's kind of similar to a square, and it's on its side. A cube root graph will look like that, won't it? Okay. Now, why are these going to be inverses? Because this one, this is your f of x, and this one over here, this is your f inverse of x, right? Why are these inverses now? They're inverses because look at what happens if I draw my line down the middle. Do these match up? Yeah, this matches here, this matches there, matches there, matches there, matches here, matches there, right? So they're inverses. We found them. And again, why are they inverses? Because when you fold it across that line y equals x, it should all match up. So I purposely picked one that we could graph, just so you could see it. You don't have to graph these. The only reason that I picked this one and chose to graph it was so you would, again, see how this is an inverse, right? We know how to graph them. I picked easy functions to graph. Let's try another one. Let's try a rational function. So let's try to find the inverse. How about we have f of x equals 4 over x minus 5. Okay. Does it have an inverse? Yes. What doesn't have an inverse? Squares. And squares sometimes can have an inverse if they give you this specific domain. But this one has an inverse. So what do? Replace f of x with y. Next, we switch them out. So x becomes y, and y becomes x. Now what do we need to do? Well, we need to clear out our fraction, and the easiest way to do that is going to be cross multiply. So we'll go ahead now and cross multiply. So that's going to give you x times y minus 5 equals 4. Distribute that x through. So let's go ahead and distribute that x through. And that's going to give me xy minus 5x equals 4. Now, what are we trying to solve for? Again, we want to solve this for y. So sometimes on these, we have to take a moment to think about what we're doing. We're solving it for y. Okay, so when we solve it for y, that means that y needs to be by itself, right? So 5x needs to be moved over. So xy equals 5x plus 4. And how do we now finish it? Yep, divide that by x, and that is our inverse. So y now equals 5x plus 4 over x, and that means my inverse of x is 5x plus 4 over x. Is everyone okay with that so far? Let's do another one. Let's do a line. So how about, we're again going to find the inverse. How about I give you f of x equals 8x minus 2. So it has an inverse, right? So let's now find that inverse. So we know it has one. What do? Replace that y, or f of x, with what? Y. So that gets changed out. And then we switch around the x and the y. And now we have to solve for y, don't we? Okay. So we're going to go ahead now and solve this for y. So what you do is replace f of x with y, switch out the x and the y. They transpose with each other. Now we solve it. So we're going to go ahead and add our 2. 8y equals now x plus 2. Divide by your 8. And now we've got y equals x plus 2 over 8, which is then f inverse of x equals x plus 2 over 8. Move it up so we can see it here. Is everyone okay with that? Now we're going to look at some of these that have squares in them. Now, a couple of them are not going to have an inverse, and a couple of them will. So we're going to be finding the inverse here, if it has one. Does this one have an inverse? No. Why does it not have an inverse? Let's graph this one real quick here. If I was to graph this function, it's a square, so it makes a u. What about the minus 2? Yep. So that's going to start about here, and then we're going to go up about 4 and over about 1. So it's going to look similar. Just a quick sketch. It looks like that, doesn't it? Now, why would this one not have an inverse? Fails the horizontal line test, doesn't it? So this one has no inverse. And is not 1-to-1. So we can't work with that one at all. However, there are some that we can work with. If I were to change it to be this, then it would have an inverse. Okay, why would this one have an inverse now? Well, what am I doing here? I'm restricting the domain. So it's going to look basically the same as far as the picture goes, right? But here's my x, and the only part I'm going to have is this part. Because that one part doesn't exist. Because we are looking at x being what? Greater than 0. And if I don't have this half, if this half is gone, right, it has an inverse now, doesn't it? Right? So you see the difference. If it gives you a restriction on the domain, it has an inverse. Now we also need to find the range. Because the range becomes becomes the domain of the inverse. So on this one, if x is greater than 0, what happens if I plug in 0? Okay, if I plug in 0, I have 0 squared, which is 0 times 4 is 0. 0 minus 2 is what? Minus 2. Now, look at that along with your picture. Okay, here's your minus 2 down here. Can y ever go below that? No, because here's my picture, right? So your y has to be greater than or equal to negative 2. We had to find that part. Okay, because that is your range. Remember, this is the domain. And this part is the range. Now, it's very important that we find that range on this one because that range becomes the domain of the inverse because they're flipped around. So let's now find the inverse of this one. So it does have an inverse because they restricted the domain because they only picked up half of it. So in that case, it really does have one. This one did not because it had no restrictions. This one has a restriction, so it has an inverse. So let's find it. So y equals now 4x squared minus 2. We interchange them. So x equals 4y squared minus 2. And we can solve this, can't we? It'll take a little bit of work, but we'll go ahead and add the 2 over. And we've got 4y squared equals x plus 2. We'll divide by our 4. X plus 2 over 4. Now, how do we get rid of a square? Square root. Now, we don't have to worry about the plus or minus case because we're only looking at half of the picture. So normally we would put the plus or minus, but we don't have to because we restricted it to only half the graph. So when we take our square root, we don't have to put the plus or minus because we've restricted it. So now we've got y equals the square root of x plus 2 over 4. So my f inverse of x is now going to be, when I rewrite it, the square root of x plus 2 over 4. And this domain, or this range here, becomes my domain. And we add on this restriction that x must be greater than or equal to a negative 2. Because your range becomes your domain. And if they give it to you, you have to keep track of it. Because we restricted the domain, so we also restricted the outcome, the range. Do what now? Yes. Because when you do the inverse, your x and your y become the opposite of each other. So we had to find our range. And the range in this case is negative 2 up higher, right? And so that range, then when you find your inverse, the range becomes the domain. And so my domain on this would now be x has to be greater than or equal to a negative 2. So it's going to be over here. And that way it'll match up. So what I'd be looking for is this. This is the entire answer because you've got to include the domain. Sure. Yep, no problem. Okay, let me get it to where we can see it all. Okay, between this one and the next one, this one has no restriction on the domain. So when I graph it, it makes a U. Because it made a U, it had no inverse. However, this one, I restricted the domain and I said x has to be greater than 0. So that means I only get this half of the picture. And if you only have this half of the picture, it passes the horizontal line test now, right? Because half of it's gone. So that's why this one is different from this one. This one has no restrictions, so it is not 1-to-1 and has no inverse. This one, though, has a restricted domain, so it's only half of the picture. And so it has an inverse. Because with the square, you can only give you half of it and it will have an inverse. Does it make sense now? So you have to watch with the squares. Just remember, if they give you a domain, if they give you this, something like that, it has an inverse. If it's unrestricted like this one and it's a square, no inverse. Okay, let's try a couple more of these. We've already done a cube. How about we do let's do a cube root. We'll do a cube root. So this is our original function here. And this one has quite a bit to it. It does have an inverse, doesn't it? Because cube roots have an inverse. So we replace f of x with y. And now we switch them out. We swap them out. Now we got to solve it. Now we don't cube yet, okay? Because we need to get that root by itself. Remember, before you cube or square, you have to make sure that you get that variable by itself. So I'm going to move that 9 over first. And I'm going to rewrite it with my cube on the left. Sorry, cube root there. So we'll write that cube root on the left. Now, once it's been moved over, now is the time to get rid of the cube root. How do we get rid of a cube root? We cube. And that gives me now y minus 4 equals x minus 9 quantity cubed. And what's my next step to finish it out? All we have left to do is add our 4. And now we've got y equals. No, we're not going to break up that cube because we're going to leave it as it is. You could break it up if you wanted to, but we really don't need to, because if we were going to graph it or something, it'd be easier to graph this way, right? We could graph it this way. But that gives you now y equals x minus 9 quantity cubed plus 4. And so now my f inverse of x is x minus 9 quantity cubed, right, plus 4. So there's my inverse. So is everyone okay with what we did? Now, you could break this up, but you don't need to. Leave it as it is. You could break it up, but that would be a lot of work. Oh, sorry. So we can see it. Okay, so there's the original. Yeah, it just had a... Yep. Okay, so we can see. Yeah, you could do all that, but we could graph this, right? We could graph this one pretty easily because it's x minus 9 quantity cubed. So that would, a minus 9, that would move it forward or to the right 9 units and up 4, right? And that would make that the inverse of the original. Let's look at one more. And I think this will probably be the last one. So let me find the sign-in sheet. So here's the sign-in sheet. We're going to look at one more, and this one is going to be very, very similar to question 6 in your homework. So let's look at question, something like question 6. So here's another one we're going to find the inverse on. And this is very, very similar to question 6 in your homework. so this one has an inverse, right? Even though it has a square, because we restricted the domain. Now, let's go ahead and find out what the range would be. We're going to look at this just by thinking about it and plugging in the 7. If I plug in the 7, what do I get? Okay, 7 squared, that makes it a 49. 49 minus 49, that makes it a 0. Now, x is always going to be bigger than 7, bigger than or equal to 7. So the smallest it could ever be when we look at our range here is going to be 0. So your range would be y is greater than or equal to 0. Because any number we plug in is always going to make it larger. The smallest it could ever be is 7. And if I plugged in the 7, I get a 0. So we need that range because that becomes your domain for the inverse. So now let's go ahead and rewrite this as y equals the square root of x squared minus 49. So we're going to interchange or swap out your x and your y. Okay. And how do we get rid of a square root? We square. So we square both sides to get rid of the square root. And that gives you x squared equals y squared minus 49. We're going to add that 49 over. Now we've got y squared equals x squared plus 49, right? And how do we get rid of the y squared? How do we make that a y? We take the what? Square root. Now we don't have to worry about the plus or minus because we've restricted the domain. And so now what do we have? We have y equals now the square root of x squared plus 49. So f inverse of x is the square root of x squared plus 49. And one more piece. What do we have to worry about? Yep. That is my range, and my range comes down as my domain. So that is now x going to be greater than or equal to 0. Is everyone all right with that so far?